Hello, this is our narrated version of the Chapter 4 PowerPoint. So this is all going to be about moisture in the atmosphere and stability. So as you can see from this picture, clearly it's being taken from an airplane, and can you tell me the type of cloud you see there in the distance? You said cumulonimbus, you are correct. So look at the flat top and you might be able to see, I guess it's to the left, maybe it's to the right, the anvil head that points in the direction of the storm. But you'll notice that this cloud is a lot taller than the other ones. That's because the cumulonimbus clouds go all the way from the lifting condensation level to the top of the troposphere. Here's an image of steam fog. Here's another image of steam fog over a lake in Maine. In one of these chapters, I guess this one, we're going to discuss the different types of fog. This is a neat little image of the water cycle from the USGS, and it's included here in the PowerPoint. If any of you want to borrow it, it would be great for the K through 12 teachers or something to show your kids. Okay, so water is so important. Gosh, let's go through all the different reasons. Most common surface material. Actually, slightly over 70% of our surface is water, common in all three of its phases: liquid water, water vapor, as in a gas, and ice. It both absorbs and releases latent heat energy or hidden heat energy during phase changes. It has high specific heat. High specific heat meaning that water takes longer to heat up, but then once it does heat up, it can hold on to that heat and it takes longer to cool down. It forms hydrogen bonds. Water, when it freezes, actually becomes less dense. Why? Because it expands, and of course we all know that ice floats. pH is 7, which is basically neutral. Water vapor, you cannot see it, you cannot smell it, it does not have a color. Water vapor does have high surface tension, meaning that it adheres to surfaces and may move by capillary action. May become supercooled. Supercooled fluid is basically just referring to water up in the clouds at higher reaches in the troposphere. Can remain in a liquid state even when it's below freezing. We'll talk more about that later in the semester. It is the universal solvent. It is a major shaper of all landforms on this planet, and of course, crucial for life. So in this image here, they're trying to show the structure of water, excuse me, in a liquid state versus frozen. Okay, so 2 hydrogen, 1 oxygen bonded together by covalent bonds, which are very strong bonds. So in the liquid state, water consists of clusters of water molecules joined together by hydrogen bonds. As the clusters move about, they continually break up and are replaced by new ones, which is why water is fluid. Now looking at the top, that's the crystalline structure of ice. Remember that ice is a mineral. Actually, that's in the earth science class, but ice is a mineral. Water molecules joined together by hydrogen bonds connect a hydrogen atom of one water molecule with an oxygen atom of another. So oxygen atoms, of course, are the red spheres. The hydrogen are the small blue spheres. And they've kept it kind of two-dimensional here, but what we're trying to show is that ice is less dense than liquid water. Notice that the molecules are spread further apart. All right, so we're looking at phase changes here. Okay, so we've got freezing, melting, evaporation, condensation, but also sublimation and deposition. We will discuss the phase changes more a little bit later on. And in every phase change, you are either going to release heat or you are going to absorb heat. As we may have mentioned before, this semester, evaporation absorbs heat. So when the air around you evaporates sweat off of your skin, it's absorbing heat and cooling your body. And then condensation releases heat, and that allows for cumulonimbus clouds to grow taller and taller as you're preparing for a thunderstorm. So these are a different, just another way to show that. These are the changes of state of water, H2O, and it's giving you an idea of whether or not you are releasing heat or absorbing heat. And it's giving you an amount in calories. I'll tell you now that we're not going to worry about how many calories are absorbed or released for our first exam. A couple other things here to mention. What is a calorie, by the way? I mean, we think about calories when we're, maybe paying attention to our Fitbit or our other fitness tracker, and are we getting our steps in? And my Fitbit will give me an estimate of how many calories I've burned in a day, depending upon how many steps I have taken. So just what is a calorie? It's the amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree Celsius or 1.8 degrees Fahrenheit. So the heat used to melt ice does not produce a temperature change. Therefore, it is latent or hidden heat. All right, question here. And of course the answer is there already. That's because my most up-to-date PowerPoints are the ones that I've created for the online class in the summer, where we don't get together at all in the classroom and discuss any of this. Okay, question. As liquid water is evaporated into the atmosphere, heat energy is what? Okay, so evaporation. Is heat energy A, released by the evaporating water? Is heat energy B, absorbed by the surrounding air? C, is heat energy given off by the water vapor? D, is heat energy absorbed by the remaining liquid? Or E, is heat energy absorbed by the evaporating water? And E is the correct answer. So the energy absorbed by water molecules during evaporation is used to give them the motion needed to escape the surface of the liquid and become a gas. And again, this evaporation of water off of your skin is how sweating cools our body. So some images here to take a look at. In the bottom left there, you see frost on a windshield. I tell you right now, I'm pretty much missing frost on a windshield. I am so sick and tired of summer. Some of you might be as well. Some of you love the heat. If so, that's great. You're living in a great place. Okay, look at the image in the top right. I don't know where this is taken. This is a bridge somewhere. Is it possibly in the San Francisco area? They do tend to get a lot of advection fog over San Francisco Bay. Anyway, you see the cars, they're driving through the fog, and then you see the warning light there on the sign that says fog. I just wonder, how close do you have to get to that sign before you can read that it says fog as you're looking through the fog? A little more about latent heat. When water vapor condenses to form cloud droplets, latent heat is released. Okay, so every cloud droplet that forms, there is some latent heat that is released. Okay, and that's released to the surrounding air, so it warms that surrounding air and gives it even more buoyancy. So when the moisture content is high, storm clouds can grow to towering heights. So of course you're talking about your supercell thunderstorms, which we tend to get in the warmer months, summer, late spring, early fall. And of course these thunderstorms can bring hail if they are supercell thunderstorms. They can bring tornadoes. We'll discuss tornadoes towards the end of the semester. So I believe what we have coming up now are going to be some different types of humidity, different ways to measure the moisture content of the air. So humidity, just humidity, with no other descriptors, humidity is just simply measuring the water vapor content in the air. All right, so again, humidity is just measuring the water vapor content of the air. So we will take a quick look at several different ways to describe humidity. Although I'll tell you right now that the only ones you need to know for your first exam would be absolute humidity, relative humidity, and dew point. Okay, so absolute humidity, definitely an exam question. It is basically the mass of water vapor in a given volume of air, or how much water vapor is in an air mass. Mixing ratio and specific humidity, we are going to leave those alone. This is an introductory class. Of course, you guys, you have access to the e-text, hopefully, and you always have access to the NOAA website or the National Weather Service website anytime you want to further explore different topics that we only briefly touch on in class. Relative humidity, definitely an exam question. Okay, so it's basically the amount of water vapor in an air mass compared to how much water vapor that air mass could hold given that particular temperature. Okay, so it's an indication of how close the air is to saturation. All right, so in other words, if you were told that the relative humidity on this particular day is 80%, and of course, as you're writing in your weather journals, should you be including relative humidity? Yes, why wouldn't you? And it does make a difference on how the air around us feels. All right, so given as a given as a percentage. So if the relative humidity in your area on any given day is 80%, it means that that air mass is holding 80% of the amount of water vapor that it could hold at that given temperature. And that would be a relatively high humidity. I think in an earlier chapter, we briefly touched on the heat index. So the heat index takes into account not just the ambient high temperature you're going to have that day, but includes the relative humidity to give you an idea of, is it going to feel hotter? So your ambient temperature might be 90 degrees, but if your relative humidity is relatively high, they might tell you that it's going to feel more like 95 degrees, and that is the heat index. And you should pay attention to those kind of things, particularly if you are going to be doing anything outside. Okay, so what is the dew point? Dew point temperature. It's the temperature to which air needs to be cooled in order to reach saturation, or in order to reach 100% relative humidity. So that is an exam question. So that picture there shows a hygrometer, which is a means of measuring. I believe that's a means of measuring the relative humidity. Yes, it is. So the original hygrometers actually were called hair hygrometers, and I believe it was horsehair that they used. And the change in the length of the hair told you something about how the humidity was changing. Was it going up? Was it coming down? Okay, this slide here, you can read about it on your own, certainly, if you would like to. And this particular PowerPoint here will run as a video. So you can stop and rewind and go back, or stop and take notes all you want to. But we are not going to touch on this for our first exam. We're also going to skip this one here. Okay, true statements here. Warm air can hold more water vapor content than cold air. So we know this intuitively from living here in the South for however many years I've lived here. And I'm sure we're going to see this on an upcoming table or chart at some point in this chapter. But capacity, just meaning how much water vapor content can the air hold, capacity is temperature dependent. So the warmer the air mass, the more water vapor it can hold, and vice versa. The colder the air mass, the less water vapor it can hold. And here is that chart table that I knew was coming soon. So on the left we have temperatures. If you want to look at Fahrenheit, they're in the parentheses there. And then there's the saturation mixing ratio. So what you see there is that as the temperature gets higher, the saturation mixing ratio is going to get higher. This is one way of showing that warmer air temperatures can hold more water vapor content. This is another one that you can read through on your own time if you would like. This slide as well is another one you can read through on your own if you would like. Although we will go ahead and discuss what is underlined there. Quite frankly, there's more information in each of these chapters than we need if we're going to attempt to cover 11 chapters in one short semester. But what's underlined there is a true statement. The relative humidity can be changed just by changing the air temperature. Okay, can the relative humidity be changed by either adding moisture or taking moisture away? Yes. But if the moisture, the water vapor content, remains constant, relative humidity can still change based on whether that air temperature increases or decreases. So, since cold air holds less water vapor than warm air, it kind of makes sense that as the temperature of an air mass drops as it cools, you're going to get closer and closer to saturation. Okay, so we have here a thermograph and a hygrograph. So the thermograph is on the top. And we may have mentioned thermograph in a previous chapter. It's basically a continuous record of temperature changes throughout a 24-hour period. And then the image there on the bottom is coming from a hygrograph. And that is a continuous measurement of humidity. Okay, so what we see there is, well, let's begin around 6 a.m. So again, it's pretty close to sunrise, just before sunrise, when we tend to hit the overnight low temperature for the day. So as you notice there in the top graph, when your temperature drops, looking at the bottom graph, that's when you're going to have your highest relative humidity, because that air mass has cooled and cannot hold as much moisture, so it's now closer to saturation than it was before. And then let's look at about, was that about 4 or 5 p.m. when you're hitting your high temperature of the day, about 5, 6 p.m. there. Now, follow down to the blue graph there for the hygrograph, and you're going to see that as your temperature rises for the day, the relative humidity is falling because that air mass is now warmer, so it could hold more water vapor, but you did not add any more water vapor. Therefore, it is further away from saturation, saturation always being 100% humidity. So we see here that there's kind of an inverse relationship here of the temperature swings throughout the day and the relative humidity swings throughout the day. All right, so some folks might be familiar with these products here. Why might you use a humidifier in the winter? Why might you use a dehumidifier in the summer? Well, okay, in the summer, that air mass can hold a lot of moisture. So you can have, a lot of humidity in the air, and you may want to try to dry that air out a little bit if you can. So a dehumidifier works very well in the summer. So in the winter, the air is not only chillier, but it tends to be more dry because that colder air just can't hold so much moisture. So in the wintertime, we might see that we have to use hand lotion more often. We might have to use chapstick more often. Dry air can really mess with your sinuses, make you have nosebleeds and so forth. So in the wintertime, some people might use a humidifier. I know you have to be careful with humidifiers. Some humidifiers, well, the only ones I've ever seen that you make use of water, okay? But the machine is also plugged in and it's heating that water, and you have to be really careful that that hot water doesn't spill on any people or animals. Okay, good question here. Which of these locations has more moisture or is holding more moisture content in the air? Okay, so we have a desert on the left and we have what is probably the North Pole or Arctic Circle on the right. Okay, so question. If the air temperature in the desert is 40 degrees Celsius and the relative humidity is 10%, so you have a 10% relative humidity in the desert there on the left, but there in the snow field, well, it's much colder. It's negative 20 degrees Celsius, but the relative humidity is nearly 100%. So which of these locations has a higher relative humidity? Well, that's going to be the snow field. But which air mass is holding onto more moisture? Okay, so the air in the snow field is holding 2 grams per kilogram, but the desert is holding 4 grams per kilogram. So while the relative humidity in the desert image there is a lot lower, it's still holding twice as much moisture content as that cold air there in the snowfield image. Okay, so what do we mean by saturation? When the relative humidity reaches 100%, then that air is saturated. And that means that we expect condensation to begin when the air hits 100% relative humidity. So this can either be at the surface, like dew on the blades of grass in the morning, summer morning, and it got somewhat chillier overnight and the air cooled enough to bring down the dew point temperature, and then you end up with condensation occurring, say, on your car windshield or on the blades of grass. And of course, this is also important when you're forming clouds and air rises and adiabatically cools, reaching the lifting condensation level, 100% saturation, or 100% relative humidity, and cloud droplets start to form. Okay, interesting concept here. I'm sure everybody has experienced this at some point in their life. You may or may not have paid attention to it, but when you're trying to hold on to your glass of, whatever, it's tea or it's lemonade or it's a white wine spritzer, whatever it is, let's say that you're sitting in an outside restaurant in the summer in the South, and you're holding on to this cold drink with a lot of ice in it. And it doesn't take long for that glass to become slimy. Why? Because there's water on the outside and then it's slippery. Okay, so why is there dew on your iced tea glass? Because condensation or dew is occurring whenever the ice and cold liquid in that glass is actually going to cool the air just surrounding the glass, cool it enough till it hits the dew point temperature. And then it's 100% relative humidity and saturated, and then condensation will occur, making your glass slippery. Okay, so this is an important slide. So what can cause changes in relative humidity, again, which is always given as a percentage, but also what could cause changes in absolute humidity? Definitely, there are some exam questions regarding this material here on your first exam. Okay, so a change in the temperature of an air mass is going to cause a change in the relative humidity. All right, so if the air mass is going to warm or become hotter, it's going to bring down that relative humidity. And if the air mass cools, becomes colder, it's going to increase relative humidity. Now, of course, adding or taking away moisture can change relative humidity. So if you add moisture content to an air mass as it moves across a large body of water, like one of the Great Lakes, that's adding moisture content that will change both the relative humidity but also the absolute humidity. So adding moisture will raise the relative humidity and also raise the absolute humidity, while reducing moisture will lower the relative humidity and will also lower the absolute humidity. And we gave an example of how you might add moisture to an air mass if the air mass moves across a large body of water. Let's give an example of how an air mass might lose moisture. We're going to talk about lifting mechanisms for the first time in this chapter, and we'll be discussing the Pacific Northwest, where you have moist air coming off the Pacific, moving across Seattle, hitting the Cascade Mountain Range, and being forced upwards. As the air mass rises, it will cool adiabatically. You will have condensation, you will form clouds, and you're going to get a lot of rainfall in the Pacific Northwest. And we know the Pacific Northwest gets a lot of rainfall. But that air mass is going to continue to move east because we are in a band of winds known as the westerlies, and they are moving from west to east. So as that air mass moves away from the mountains, it has lost most of its moisture because it, formed clouds and it rained there in the Seattle area and the mountains, and that air mass has now lost moisture as it moves over to the leeward side of the island. So that's an example of an air mass losing moisture content. By the way, that can create what we refer to as a rain shadow desert on the leeward side of a mountain range. All right, so a little bit more about humidity. By the way, there might be some, I think this chapter has some repeats here and there. So when there are slides we just don't need because we've already talked about it, we'll just go ahead and skip it. But we can go ahead and recap here. So humidity is just simply referring to the amount of water vapor in the air. That's humidity, not relative humidity. Air that is saturated is filled to capacity with water vapor. Something I mentioned earlier in this presentation, capacity is temperature dependent. Warm air can hold a lot more moisture than cold air. So when you add water vapor to an air mass, that's actually going to add pressure to that air, and then we're going to refer to that as vapor pressure. Okay, this is a nice table. This is better than the table we looked at earlier. So here you have your temperature. Degrees Fahrenheit is that second column from the left. And then over on the right, that's just letting you know how many grams per kilogram water vapor can be held in that air mass. Okay, so let's look at 0. We don't have a 0 in Fahrenheit, do we? That's okay. Let's look at 0 degrees Celsius, 32 degrees Fahrenheit, freezing. That freezing air mass can only hold 3.5 grams per kilogram water vapor. How about 77 degrees, which is a very nice temperature to be walking around outside. That air mass is warmer and can now hold 20 grams water vapor for every kilogram of air. How about when that air temperature reaches 95, you can now hold 35 grams, and 104, you can hold 47 grams. So if we were to plot this, this would not be a linear function. It would not be a straight line. Okay, so as the air mass warms, it can hold a lot more water vapor. Okay, just a little bit more emphasis here on relative humidity. Okay, so remember that relative humidity is basically a ratio of the air's actual water vapor content compared to how much water vapor it could hold at that particular temperature. It's always expressed as a percent. And if that air is saturated, that's the same thing as saying that you have 100% relative humidity. You have reached saturation, as much moisture content as that air mass can hold at that temperature, and you should expect to see condensation. Okay, ways to change relative humidity. This just kind of expands upon something we talked about a few slides back. Changes in moisture content can change relative humidity. If you're going to add moisture, it's going to raise the relative humidity. If you're going to remove moisture, it's going to lower the relative humidity. But you can change the relative humidity without adding or removing any moisture, only if you have changes in air temperature. That's all it's going to take to change humidity. So if you lower the temperature, it's going to raise the relative humidity, and of course the opposite of that is true as well. If you raise the temperature, it's going to lower the relative humidity. We saw that when we looked at the image of the temperature swing throughout the day and the relative humidity as a percent change throughout the day. And remember, they were mirror images of each other. We're going to skip. Dew point temperature, an important concept. Okay, so the dew point temperature is the temperature to which a parcel of air or an air mass would need to be cooled to reach saturation. So if that air mass is cooled to or below the dew point temperature, well, then it's going to reach saturation, it's going to reach 100% relative humidity, and condensation should occur. Okay, so what kind of condensation? Well, cloud formation, fog, which is basically a cloud at the ground surface, and dew. All right, so by the way, in parentheses there, when you're looking at a cloud outside, when it's a cloud, that's no longer water vapor. Those are either droplets of liquid water or ice crystals. Some clouds might have both of those. Now, to have condensation occur, so not only do you need that air mass to be cooled to the dew point temperature, but you need a surface for that water to condense upon. It could be your car windshield, the blades of grass, your glass of iced tea or lemonade at the restaurant. Okay, here's an interesting little thing about the dew point temperature. So this is something that the folks on the Weather Channel really like to talk about. So the dew point temperature is not only the temperature at which that air mass is going to be saturated, and you should expect condensation to occur, but your dew point temperature for the day is going to give you some idea of, is the air going to feel decent? Is it going to feel humid? Is it going to feel really, really bad? All right, so for every 10 degrees Celsius or 18 degrees Fahrenheit increase in air temperature, the amount of water vapor needed for saturation doubles. So, dew point temperatures above 65 degrees Fahrenheit, the air is going to feel humid. Dew point temperatures above 75 degrees Fahrenheit, the air will feel oppressive. Sometimes on days like that, they might describe it as, you're leaving where you live or where you work or go to school, and it's temperature controlled, and then you walk outside and it's like somebody walked up and wrapped you in a wet blanket. That's kind of what we mean when we describe the air as oppressive. So this is similar to something that we looked at in an earlier set of graphs. I think I like it better here where they put the two graphs on the same image together. So here you're looking at the temperature swings throughout the day. Low temperature overnight, the high temperature there in the afternoon, and you're looking at how the relative humidity changes throughout that 24 period. And again, you'll notice when the air temperature drops, relative humidity goes up. When the air temperature rises, relative humidity goes down. So, are they going to tell us what time this is for? No, this is just for discussion purpose. This could be any day. Maybe we can look at this and figure out what the season is. All right, so the question, why are dew point temperatures part of our daily weather report? What do we see on this map? You see that red L? That's a low pressure system. The two H's are high pressure systems. The L there, the low, is associated with the mid-latitude cyclone, something we'll talk about in a later in a later chapter. I love to talk about mid-latitude cyclones. And then you see the warm front and the cold front there associated with the mid-latitude cyclone. So you see some dew point temperatures. Well, also we're seeing isobars. See those numbers across the top, 1008, 1016, those are isobars, which are going to connect points of equal air pressure. And then you see some dew point temperatures listed there. So on the key, they show us that it's the number on the bottom that is the dew point temperature. So I want to point out South Florida, You got some dew point temperatures there of 74, 75, and 77. So notice the air temperatures above that. Your air temperatures there are 75, 76, 81, which really, those are not horrible air temperatures, but they're having a humid day there. Okay, why do I say that? Because their dew point temperatures 74, 75, 77. As far as humidity goes, it's going to feel oppressive for them that day. All right, so here's another way to show dew point temperatures. This is mid-September. This is back in 2005. Dew point temperatures above 60 dominating the southeastern United States. So as we looked at in a previous slide, if the dew point temperatures are 65 or higher, it feels humid. If they're 75 or higher, it feels oppressive. Wow, notice the desert southwest there. Look at those low dew point temperatures. I don't know if any of you have ever visited, traveled, or lived in the desert southwest, but it's different. So temperatures there can be, higher temperatures than we might experience that same day in North Carolina. But it's a dry heat. It's different. It's really kind of hard to even describe. It's easier to handle the heat out there when the moisture contents are so low. All right, dew point thresholds. Oh, this is a really interesting table, and I'm glad that it's in Fahrenheit. I mean, that's what we continue to use in this country. That's what we're used to. Okay, so if the dew point temperature is really low, like less than 10 degrees Fahrenheit, it says significant snowfall is inhibited. If the dew point temperature is greater than 55, you need that as a minimum to develop any severe afternoon, evening thunderstorms. Again, if it's greater than 65 or equal to, considered humid by most people. If it's greater than or equal to 70, typical of the rainy tropics. There are days when I feel that Southern Pines is like a rainforest, and I'll complain about it. If the dew point temperature is greater than or equal to 75, then it is considered oppressive by most. See that question there in yellow? I think that's an extra credit question on your first exam. Does it ever get too cold to snow? What does that mean? Okay, so the answer to that is yes. It can be too cold to snow, meaning that it's so cold and that the air mass is not holding much moisture. You have a low dew point temperature. Basically, that's just telling you that the air is so dry it's not going to snow. So there are days that it's really cold and you think it should be snowing and it looks like winter and it feels like winter, but it might just be too cold to snow, just meaning that the air is too dry to snow. Okay, so measurements of humidity. So I think now we might go through some images here of different types of hygrometers. So this is your old-fashioned hair hygrometer. So horsehair has been used in the past. I believe they use human hair as well. Okay, so sensitive to changes in relative humidity. Hair expands as humidity rises, contracts as humidity decreases. We kind of know that from living here in the South where we have high humidity. You know, there are some days that your hair is just, my hair anyway, is just going to frizz no matter what. I don't even try to make it not frizz because I feel it's a losing battle. Anyway, so the hair hygrometer is attached to a hygrograph, which looks kind of like a seismometer, giving you a continuous record of humidity changes throughout the day. But this is kind of old, okay? Why? Because it's slow to respond to changes in humidity. Got to calibrate. An electric hygrometer, this is much more advanced, uses a plate coated with carbon. Electrical resistance of the carbon coating changes as the moisture content of the air changes. And this can translate into a relative humidity, which you see there in that image, 53%. And some types of these electric hygrometers are used in radiosondes, which are those things that the weather balloons will take up into the troposphere to gather data. By the way, you're not going to have to know any of these measurement instruments for your first exam, but they are fun to look at. This is a sling psychrometer. We have, or we used to have, maybe a small handful of these. And I used to occasionally have the lab students, we would go outside and we would actually try to measure the relative humidity, but we don't have very many of these things, and the little sock thing you see there hanging off the end of it, we don't have enough of those to go around. We certainly don't have enough to do this together in class. And these days, well, I don't know, I guess it'd be something fun to do outside, but we're just not going to do it. But it was kind of a neat thing, using a wet bulb and a dry bulb and looking at these two different thermometers, and then you use it in conjunction with a table of data, and it's an old-fashioned way to be able to tell what the relative humidity is, and you could compare it inside versus outside. Okay, we're going to skip this. We're going to skip this. We're going to skip this. And we'll skip this. All right, so remember the heat index, also called the heat stress index. We did talk about this in a previous chapter. I don't remember which one, maybe chapter 1. But just a reminder here, you have air temperature over there on the left, and across the top you have the relative humidity. And yeah, you can just kind of, look at what your, average, or just choose a particular air temperature, and then look at, what percentage of relative humidity is it going to take to make a person in danger, extreme danger of heat stroke. Okay, so it's also color coded there. Where it's in yellow, caution, you could get fatigued, be careful. Lighter orange, extreme caution, risking muscle cramps, heat exhaustion, perhaps sunstroke. In the darker orange, danger, muscle cramps, sunstroke. And then of course in the darkest orange, extreme danger and heat stroke or sunstroke are likely. So in other words, if you were, say, on a trip to Las Vegas with your friends and your ambient air temperature that day was 108 degrees, while it's going to feel like a drier heat than 108 degrees would feel like in North Carolina, it doesn't take much of humidity. Just a 40% humidity is all it takes to make it very dangerous to be outside doing any kind of physical activity. Evening condensation. Okay, so the sun sets, we're no longer bringing in that short wavelength radiation, and we're starting to lose that terrestrial re-radiation that the Earth spit back out and that the greenhouse gases trap. So we refer to that as radiation cooling, the ground losing heat in the evening and overnight. Radiation cooling. So that can provide dew on the grass or on your car windshield. Another example of evening condensation, fog may form slightly above Earth's surface as this radiation cooling is happening because the air at the bottom has cooled enough to hit the dew point temperature and to allow for condensation. Adiabatic temperature changes. I have probably used this term before in these narrated PowerPoints, adiabatic. All that means, adiabatic just means that you're going to change the temperature without adding heat or subtracting heat. So you're going to change the temperature, either warming or cooling, by either expanding or compressing the air. Okay, so let's begin with the first bullet there. Air that is compressed, meaning it's being squeezed, is warmed without adding heat. So it's warmed by compression. Okay, what kind of air mass is going to do this? A dense air mass that is therefore sinking. The air molecules are going to be compressed together. So what happens is the air molecules, as they're being compressed together, they are then moving faster. They're also under higher pressure. They're moving faster, so the temperature rises. So that air mass is warming without adding any actual heat. Second bullet. Air that expands will cool without subtracting heat. So, and then that third bullet there is an example of that. So when you have a warm air mass rise in the troposphere, like a hot air balloon, as that warm air mass is rising, it's gonna hit areas of lower temperature. Remember that temperature decreases with altitude in the troposphere. So as that air mass hits regions of lower temperature, and therefore lower pressure, that lower pressure is the most important, the air is going to expand, just simply meaning the air molecules will move further apart. So that is adiabatic cooling. So a rising warm air mass, as it's rising higher and higher, it is under less and less pressure, therefore the molecules spread out. That is adiabatic cooling. And that can lead to cloud formation. Okay, so bottom line from that previous slide, when air is compressed, it warms, as in a sinking dense air mass. When air expands, it cools, as in a rising air mass. Okay, so for condensation to occur in a large enough numbers that you can form clouds, well, the only way you're going to get a significant amount of air to cool to its dew point is by some kind of lifting mechanism. Okay, so cloud formation requires not only some water vapor in that air mass, but some kind of lifting mechanism so that the air will therefore rise and expand and cool adiabatic. Okay, so this image here is actually representing a relatively stable air pressure system, or it's representing stability in the atmosphere. But we're going to keep it simple. So what do you have there? You have this hot pocket of air at the surface, 32 degrees Celsius, that's Celsius. And that hot pocket of air is warmer than the surrounding air, so it's going to rise like a hot air balloon. And as it rises, it's going to cool because it is simply expanding. That's why they're showing those balloons looking bigger as you move on up. Now, here we're looking at the lifting condensation level. We are looking at cloud formation. We might classify that cloud as cumulus humulus or cumulus congestus. Okay, so rising air, or warm air mass, is rising, but it's expanding as it rises. Therefore, it's cooling adiabatically. It's going to cool at the dry adiabatic rate of 10 degrees Celsius cooling per 1,000 meters until the air reaches the dew point, and then condensation occurs and cloud formation begins. Okay, so notice on the drawing there you see something called the lifting condensation level. That's the altitude in the troposphere at that time and place where the air has cooled enough for condensation to be occurring. Now, can you get the air to continue to rise? Well, sure. If that air is still warmer, that air mass that's been rising is still warmer than the air around it, it will continue to rise. But you know what? As it's rising, it's cooling, it's hitting the condensation level, and condensation is occurring. It's going to release latent heat. And this release of latent heat from condensation is going to reduce the rate of cooling. So we're going to see that there is a dry adiabatic rate, or the typical amount of cooling that we expect with an increase in altitude, and then there's also a wet adiabatic rate. And the wet adiabatic rate does not kick in until you reach the lifting condensation level. But that last sentence down there in italics, make sure you get that written down in your notes. That's definitely an exam question. The wet adiabatic rate is always less than the dry adiabatic rate. Why? Because of condensation releasing latent heat energy. Okay, so what we have here is the dry adiabatic rate. This is just another way to describe the environmental lapse rate. And I know that I gave you guys an average environmental lapse rate in a previous chapter, and I asked you to know that for your first exam. All right, and why is it an average? Because it can vary, okay, and it has to do with this dry adiabatic rate and the wet adiabatic rate. So let's discuss these first, then I'll tell you what you need to know for your exam. All right, so the dry adiabatic rate, and we'll go ahead and keep it in Fahrenheit, if the air is dry and you haven't hit the lifting condensation level yet, every 1,000 foot of increase, it's going to cool by 5.5 degrees Fahrenheit. But once you hit the lifting condensation level and condensation is occurring, releasing latent heat, then that lapse rate is going to lower. Okay, so the wet adiabatic rate is somewhere between 5 degrees Fahrenheit and 1 degree Fahrenheit of cooling for every 1,000 feet that you go up. All right, so what I want you to know about this for the exam is simply that the wet adiabatic cooling rate is always less than the dry adiabatic cooling rate. All right, so adiabatic cooling. Rising air cools at the faster dry adiabatic rate from the surface up to the lifting condensation level, at which point the slower wet adiabatic rate will take over. Now, on a previous slide, I reminded you guys of something that we talked about in either Chapter 1 or Chapter 2, the average environmental lapse rate. Remember that? So for every 1,000 feet that you go up in altitude, you should expect cooling of 3.6 degrees Fahrenheit. Or for every 1,000 meters or 1 kilometer that you go up in altitude, you should expect cooling of 6.5 degrees Celsius. Okay, so sometimes it is more, sometimes it is less, sometimes it increases with height if you have an inversion. Okay, so the environmental lapse rate is an average. It can vary, and it is different than the adiabatic rates. And again, for the adiabatic rates, please just know that the wet adiabatic rate is always lower than the dry adiabatic rate. Yay, we're finally to lifting mechanisms. So at whatever point in our in-class discussion, actually we might get to this next week because we have very little of Chapter 2 that we're going to cover together. We're going to get to the lifting mechanisms. I really like this, and we might have some drawings on the board. Okay, so we're going to begin with the one that involves mountains, orographic lifting. Okay, so what happens here, there's the Coast Ranges and the Sierra Nevada. So we're talking Northern California. So Northern California, West Coast here, you have air moving off of the Pacific heading east. Okay, why is that here? Air heading east? Because we're in a band of winds known as the westerlies, meaning the wind is blowing from the west. So our weather patterns in general are moving from west to east. So that moist air blows off the Pacific and into the west coast there of Northern California, and it's going to have a little lifting there on the Coast Range, but when it hits the Sierra Nevada batholith, big mountains, you're going to have a lot of lifting. You see the blue arrows there moving up. You're going to have condensation. You're going to have clouds form, and it's going to lead to rain. And then as that air continues to head east and moves off of the mountain range, it's now very dry. You see that in the purple and orange arrows. So that can form what we refer to as a rain shadow desert. So the windward side of the mountain is the side of the mountain that is getting the winds blowing on it. You see that in the dark blue arrows. And then the leeward side of the mountain range is the other side. You see that with the purple and the orange arrows. So then the photos there are corresponding. The photo on the left, which shows the sequoia forests, you expect to find that there in the mountains on the windward side. And then what do you have on the leeward side? You have a rain shadow desert, this one known as the Great Basin Desert. So this orographic lifting, it's one of our lifting mechanisms. It involves a mountain range. Orographic lifting can lead to a lot of precipitation. So what are we looking at here? Heavy snowpack along Trail Ridge Road in Colorado's Rocky Mountain National Park. Look at that. That's just crazy ridiculous. Of course, you know, who knows how old this image is. Look at those cars. I'll be honest, I think those cars are from the late 80s, maybe. I wonder if they even get quite as much snow anymore in the mountains of Colorado. So, California's Death Valley is another example of a rain shadow desert. By the way, and this is fall of 2020, and the other day they nearly broke a record in Death Valley, and the temperature reached 130 degrees Fahrenheit. I think that was this past Sunday. So that air is very dry because it lost all of its moisture on the windward side of the mountain range. So here's just another diagram of the orographic lifting, showing you temperature changes there in degrees Celsius, showing clouds forming, dumping a lot of rain on the windward side there on the left, and then the dry air racing down the mountains on the leeward side over on the right. And as that air, not only is it dry, but as it's sinking, it's warming adiabatically. Rain shadow desert. This is a neat little graphic that I like to show in class. I don't know if we'll have time or not, but you see there Washington State. So not only do you have the Cascade Mountains, which are very famous because of Mount St. Helens and Mount Rainier, but you see the Olympic Mountains over there on the big peninsula there. So, and then of course you have your annual precipitation. So it's color coded, you know, in the lighter yellow, that's less precipitation. You get up to darker greens and blue, greater precipitation. And you see a clear pattern there, don't you? You see that in the mountains, you're getting more precipitation than in the valleys, and you're getting a lot more precipitation than you do in the rain shadow desert that is to the east. Frontal wedging. This is also maybe referred to as frontal lifting. This is another type of lifting mechanism. I don't know if it will show us every type of frontal wedging or not, but this is what we're looking at here. And I don't know, I kind of like the image on the bottom right a little bit better. Look at either image you want to. They're both pretty good. So let's say that Pembroke is there in the blue, where you have a cooler air mass over top of you. Don't we wish? But you got a warm front coming in. You got a warmer air mass coming in from the west, and that frontal boundary there is where the blue wedge kind of touches the ground. So what you have is the warm air being forced up and over the cold air mass because the warm air mass is less dense. So we could say that that wedge of cold air there acts like an invisible mountain range, and this is another lifting mechanism, and yes, this can lead to condensation, rain, and perhaps even afternoon thunderstorms. So here's just another way to look at that. So again, in frontal wedging or frontal lifting, when you have a warm air mass coming in to try and overtake a colder air mass, that cooler air mass is going to act like an invisible mountain range, push the warm, moist air up and over it, leading to condensation and perhaps precipitation. Then there's convergence, and they're showing this in Florida because Florida is, well, certainly in this country, the best example of convergence. So Florida is basically a big peninsula. You know, it just kind of sticks out there into the Atlantic and Gulf of Mexico. And a good example of this would be daytime heating in the warmer months. So remember that land will heat up more quickly than water. So what happens is that you get a lot of heating there on the land, on the peninsula, and that hot air rises. It's going to cool and condense and can form these cumulonimbus clouds and thunderstorms. But how are you bringing this air in from the Atlantic and the Gulf of Mexico? And the answer is that that daytime heating and rising air over the land creates low pressure. So you have higher pressure offshore on either side of Florida and lower pressure there in the Florida Peninsula. And winds always blow from high pressure to low pressure. So the winds are coming in both from the Atlantic and the Gulf of Mexico. So this just adds to the lifting, all right, because you have the two air masses moving towards each other and there's nowhere for them to go but up. This is really neat. Okay, so this is back when we had a space shuttle. This is an image of southern Florida from the space shuttle. And I personally can't see the actual land here, but you get an idea of where the Florida Peninsula is because you can kind of trace it out with all of those clouds. Okay, so warm days convergence, again, air coming from the Atlantic and from the Gulf of Mexico converging and pushing upwards. Another lifting mechanism giving you condensation and precipitation, helping to generate many mid-afternoon thunderstorms. And then there's something we might refer to as localized convective lifting or just convection. Okay, so let's begin on the left. You see a plot of land, and you see that the one in the middle there is different. Maybe they burned it on purpose because that's going to help do something with the next crop. So it's a different color, it's a darker color, therefore it's going to absorb more solar radiation, therefore you get a hot pocket of air over that parcel of land. And then that pocket of air is warmer than what's around it, so it's simply going to rise, it's going to expand, notice the bubble getting bigger, it's going to cool adiabatically, you're going to get condensation, and you're going to build a cloud. So this is localized convective. So as long as air is warmer than its surroundings, it will rise, just like a hot air balloon. All right, are we done with this PowerPoint yet? I don't know. I never do this PowerPoint all at once. Normally we could take at least a couple class days to get it done. All right, so now we're going to briefly discuss stability, and then I'll let you know towards the end of this presentation what I want you to know about stability for the first exam. In a stable atmosphere, an unsaturated parcel of air will lift if it's warmer than the air around it. It will lift, but it will expand and cool adiabatically at the dry rate, which is a set rate, of 10 degrees Celsius per 1,000 meters. Okay, but the temperature of the rising air parcel is lower than that of the surrounding environment. Then it will just allow itself to sink back down to its original position. Okay, so what you're looking at here is, what is the control over a stable atmosphere or an unstable atmosphere? What is the control over whether or not this air mass will rise up and then just sink back down, or rise up and start condensing and continue to rise and build a thunderstorm? And the answer there is that while the dry adiabatic rate is fixed, that environmental lapse rate, look at the top left corner of the figure there. Remember that the environmental lapse rate is an average. It actually varies. So whether or not your air is stable or not depends on what the environmental lapse rate is doing at that time. And in this case, it's 5 degrees per 1,000. Okay, so absolute stability. Again, we're going to go through these slides, and then I will let you know what I want you to know about this for your exam. So we're going to discuss it, whether it's on the exam or not. Absolute stability. This occurs when the environmental lapse rate, which again is an average and can vary a little bit, is less than the wet adiabatic rate. Okay, so the most stable conditions exist when the air temperature increases with altitude, a temperature inversion. And when can that happen? You know, these things are pretty temporary. They don't stick around all that long. But sometimes you can get a temperature inversion if you have intense radiation cooling at the surface on clear nights, when you don't have cloud cover there to help trap that heat. So what are we looking at here? We're looking at our dry adiabatic rate of 10 degrees Celsius per 1,000 meters, and we're looking at a wet adiabatic rate of 6 degrees Celsius per 1,000 meters. But again, in the top left corner, the average environmental lapse rate right now in this situation is 5 degrees Celsius. So the environmental lapse rate is less than the wet adiabatic rate, and that can lead to relatively stable conditions. In other words, you're not expected to get precipitation, certainly not expected to get a thunderstorm. Okay, absolute instability. Now it's getting fun. Now you notice that cloud getting taller. Okay, so what happens here? Absolute instability occurs when the environmental lapse rate, remember that can vary, is greater than the dry adiabatic rate. So what does that mean? It means that the air mass is always warmer than the surrounding air, so it will keep on rising. As it keeps on rising, it's going to keep on cooling adiabatically, and you're going to have more and more condensation, and that condensation adds some heat to that air mass so it can keep on rising, so you can build this cumulonimbus cloud going all the way to the top of the troposphere. Okay, so again, you've got your dry rate, which is fixed, dry adiabatic cooling rate, 10 degrees Celsius per 1,000 meters, and then above that, above the lifting condensation level, you have the wet adiabatic rate here, which is always less, and here it is 6 degrees Celsius per 1,000 meters. And then you look at the environmental lapse rate in the top left corner. And again, remember that this environmental lapse rate can vary. In this scenario, it's 12 degrees Celsius per 1,000 meter. So as that moist air mass there in the middle keeps on rising and having more and more condensation, releasing more latent heat energy, that air mass continues to be warmer than the surrounding air, so it's going to keep on rising, and it can build a cumulonimbus cloud and lead to a thunderstorm. Conditional instability. This occurs when moist air has environmental lapse rate between the dry and wet adiabatic rates. The atmosphere is conditionally unstable when it is stable with respect to an unsaturated parcel of air, but unstable with respect to a saturated parcel of air. Okay, so we're going to leave that one alone. I'm running out of steam. I believe on our upcoming slides, I'm going to give you the lowdown on what I want you to know about a stable atmosphere versus an unstable atmosphere. We are going to skip this. We could go ahead and take note of this. So again, remember that the environmental lapse rate will vary. It's not fixed. The adiabatic lapse rates, are fixed. The dry rate definitely is fixed, but the average environmental lapse rate, it can vary, and the greater the environmental lapse rate, the more unstable the atmosphere, meaning the greater the temperature drop with an increase in elevation, the more unstable the atmosphere. Why? Because that cloud condensing, adding heat to that air mass, as it keeps rising, it's still warmer than the surrounding air because the environmental lapse rate there is high, and you can build a cumulonimbus cloud. All right, jumping around a little bit because I'm just kind of taking a look here at what I might want you to know for the exam. Okay, so stable profiles, temperature decreases gradually with altitude, most stable when a temperature inversion occurs. Okay, so stable profiles occur when you have, say, cooler air at the surface and warmer air aloft, like a temperature inversion, perhaps due to radiation cooling on a clear night. All right, unstable profiles. When you have warmer air at the surface and cooler air aloft, which is what we expect, right? We expect a decrease in temperature with an increase in altitude in the troposphere. Okay, so this slide, I'm going to want you to know this material here for your first exam. So you're not going to have to know the specifics about conditional instability, absolute stability, absolute instability. I'm just going to maybe want you to be able to recognize what kind of things can enhance instability, what kind of things can enhance stability. So let's begin with what can enhance instability or make for an unstable atmosphere. Intense solar heating, warming the lower part of the troposphere. Okay, advection, which is the heating of an air mass from below as it passes over a warm surface like a warm body of water. Advection can enhance instability. A lot of solar heat can enhance instability. What else? Third bullet, general upward movement of air. In other words, lifting mechanisms can enhance instability. That makes sense. But then also something we haven't talked about yet, radiation cooling from cloud tops. Something that can be seen from weather satellites. So let's talk for a second about radiation cooling of cloud tops. Not on your exam, but let's discuss it because it's cool. So the loss of heat by radiation cooling from cloud tops at night can add to their instability and vertical growth. In other words, you're releasing heat with that condensation. So cloud droplets emit heat energy to space. This deepens the lapse rate near the tops of these clouds and can allow for additional upward flow of warm air. So sometimes you get these nocturnal thunderstorms or these overnight thunderstorms forming from these clouds. And maybe when the sun went down, the clouds didn't look like they were going to do anything. And then at 2 a.m., you're finally asleep and you got to get up early and have a long day the next day. And now there's this violent thunderstorm and all this thunder and lightning, and it wakes you up. That is from radiation cooling of cloud tops. Okay, so what can enhance stability? All right, so radiation cooling at Earth's surface after sunset can enhance stability. Advection, the cooling of an air mass from below as it moves across a cold surface like a snow-covered field. And then just general subsidence or sinking within an air column. These things can enhance stability. You will be getting a study guide. It's already on Canvas, but I will bring hard copies at some point. And there's a lot of material on this exam. I do recommend, working on that study guide to get you ready for it. Okay, so what do stability and instability look like out there, just taking a look at the sky? All right, so when stable air is forced aloft, if you get clouds to form, they'll be widespread, they won't have much vertical thickness, and you either won't have any precipitation or you might have some light to moderate precipitation. So this might happen when you have a warm front moving in. But that warm air mass moving in isn't that much warmer than the air mass you had there before. So you have some lifting, but the air is still relatively stable. So clouds associated with unstable air, what does that look like? Well, you know what that looks like, okay? That looks like the clouds that are growing, something that we will refer to as cumulus conjustus in a later chapter, or of course your cumulonimbus clouds associated with heavy rain and perhaps thunder. Okay, so what do you think, guys? Looking at this picture, what does that tell us about this atmosphere? Is it stable or unstable? Okay, and what kind of cloud is that? Well, it's a cumulonimbus cloud, of course. So this is going to be, yes, you guessed it, unstable.